I'm Dr. Numan again from COMSOC, and I'm going to introduce another seasoned speaker, you can say, and expert, Dr. Dilip. So he is today Dr. Dilip Krishnaswamy. So he is a Vice President in New Technology R&D in Reliance Industry Limited. He is working on microservices-based platform for applications on new technologies such as blockchain technology, machine learning, and 5G. This work is currently nominated for the Fall 2020 Enterprise Blockchain Award. He has worked prior to this as a senior scientist in IBM Research. He has also worked with Qualcomm. He has worked with Intel Corporation earlier. He has been granted over 60 granted US patents, and he has to his credit 70 plus peer review publications in journal and conference proceedings. Patents granted normally in the area of machine learning, personalized recommendation engine, wireless networking, communication, self-aware system, cognitive processing, IoT, M2M system, video processing, and so on. So he's going to talk about blockchain and quantum processing. So I'm not going to read his profile. If you go to his Google site, you find some 20-22 pages. So this is very big to Dr. Dilip. So he has been the chair of COMSOC last year, and he is very active IEEE volunteer as well. So many conferences, general chair, still in 5G. World Forum, he is a TPC chair, and if you have not submitted, some of the workshops are still open, you can submit your papers. So with this small introduction, I hand over to Dr. Dilip. Dr. Dilip, thank you very much for speaking with us and audience and giving your expertise on blockchain and quantum processing for 5G and beyond. Over to you, Dr. Dilip. Thank you very much.
Thank you, Naveen. Yeah, actually, the 5G World Forum, I think the technical papers deadline is passed, but there are some workshops, and I think the deadline is 17th of June. So there's still time to submit to the workshops. So, yeah, so this talk, thought I'll talk about quantum and blockchain, and I put quantum first there because I'm not sure how much time we'll have, and I think many of you probably listened to my blockchain related stuff, so maybe I'll just touch upon it briefly in the end if we run out of time. But the motivation for this is that the emerging infrastructure is distributed, hierarchical, cloud data centers, in-network data centers, edge data centers, and all of that. And there's all kinds of microservices running in all of these data centers, interacting with each other, and so on. So it's going to be very interesting going forward, and you can have different kinds of applications running in this kind of virtualized infrastructure. And I believe that on June 20th, Subodh might lead an SD and NFV kind of discussion. So please be tuned for that. There's this trend towards disaggregation with microservices, but it's not just microservices for network functions to realize the infrastructure itself, but also all kinds of applications, whether it's artificial intelligence, machine learning, blockchain, quantum-inspired algorithms, and so on. So you can imagine that when needed, you might invoke a blockchain-related microservice, or you might invoke a quantum algorithm where you could interact with an actual quantum computer, or maybe the algorithm itself is just quantum-inspired. So we could think along those lines. And so now, yeah, let me start with quantum and see how far we go. And I thought I'll just introduce some aspects related to the physics of these systems, and also bring in the computational aspects. I'm going to focus more on the computational aspects, and we have a couple of experts in our COMSOC group. Anand from CDOT will talk about quantum key distribution algorithms in the near future, and Dr. Gana will talk about error coding in the quantum realm. So be tuned for those lectures also in the future. But I thought I'll try to give you an introduction to this area to kind of set the stage for any of those discussions. So the most interesting experiment that started it all was the double slit experiment, not the Young's double slit experiment, if you're familiar with it from high school and stuff. So you may have photons or electrons impinging on a screen which has two slits, and then there's a screen at the back where you actually observe, and it turns out that you get an interference pattern, and you can say, okay, there's a whole bunch of photons, and some photons go through one slit, and some photons go through the other slit, and they interfere with each other, and you get the interference pattern. And normally, when we study physics with Resnick and Halliday, we just write the interference between those two paths and say, hey, here we got constructive, here we got destructive interference, and so we get these bands. But the more interesting aspect to this is that, okay, you can say there are multiple photons, but what if you just send one photon at a time, or one electron at a time, or one molecule at a time? You will still get this interference pattern, which is quite magical. It's as if a collection of photons, electrons, or even molecules can know that they have to collectively produce this interference pattern, which is very, very interesting. And they don't split up into parts such that one part goes through one slit and goes to the entire electron shows up at one spot on the screen, but the group of electrons would or a group of photons would produce this interference pattern as they come one after the other, which means, you don't know. So people start wondering, is it a wave? Is it these particles? How are they working? And so the answer is neither, but quantum mechanics and quantum physics tries to explain this kind of phenomenon with mathematics. So we'll try to see what this means. What we do in this domain is to say that each of these quantum particles are in a superposition of states. And when the particle is observed on the screen at the back, a measurement happens that collapses the state of the particle. So to one of the states in that superposition. So it could be like if the photons could be spin up or spin down, or electrons could be spin up or spin down kind of thing. But when you observe, you'll observe only one of those states. So some background on the physics related to this. Familiar with Planck's constant H? You can say E is h nu, right, or hf. Energy is Planck's constant of frequency. It's also equal to h bar omega, where h bar is a reduced Planck's constant h by 2 pi, and omega is angular frequency equals 2 pi f. So these are two different ways of writing that equation. And de Broglie's equation also you might be familiar, lambda equals h by p, but you can write p is h by lambda, or you can write p is h bar k, where k is 2 pi by lambda. So typically we use the h bar equations in the math here. So, but now let's say you have a particle, a quantum particle, and it has some kinetic energy. Let's say that's half mv square. You can also write that as p squared by 2m, where p is the momentum, mv. Now let's say you write the phase velocity. Velocity is frequency times wavelength, right? That can be written as omega divided by k, because k is 2 pi by lambda. So And now if you multiply by h bar, you get h bar omega by h bar k, which can be written as E divided by P. But if you convert that, you get half mv square mv. And so you get V equal, so velocity is velocity by 2. And well, what's going wrong here? You know, it looks funny, right? But actually what is postulated here is that there is actually a group velocity that is has to be considered here, and that the velocity of a particle is the group velocity of a packet constructed by a superposition of waves. That is, the omega that we have is not a discrete value, it's a continuous value. Omega will be a function of k, the wave number, and k is 2 pi by lambda. So, but think of omega as like having some sort of a Gaussian distribution, but a very sharp peak around a certain value. So then, you know, if you had a discrete value for the frequency, that would be that peak, but it's actually distributed around that peak. Okay? And now, if you think of it that way, then omega is actually a continuous variable, and you differentiate it and you multiply, say, so you take d omega by dk, that is called the group velocity, and you multiply by h bar for the numerator and denominator, and then h bar omega is E and h bar k is P, so you get dE by dP, and now you get the two canceling out because you have derivative of P squared by 2m divided by dP. So you get P by m, and that gives you V. So that's the group velocity, and so these particles are actually, you know, moving as a group, as a superposition of waves. So, and that is called a wave function for the particle, psi of x comma t, and you can write that as integral dk, phi of k, which is equivalent to the amplitude, times that e raised to I kx minus omega t. Now, so you know, if you had this as a delta function, then you would pick out k at some value k naught. But it's actually some sort of a smooth function. So you integrate over it to get the wave function. So think of it as a superposition instead of the integral. If you think of having a sigma there, then that sigma is adding up multiple waves, right? Each wave would be e raised to I kx minus omega t, where you have a slightly different omega and you're combining them. And in the limit, the summation becomes the integral, right? So now, we said, okay, let's think of this omega as some sort of a Gaussian distribution, which is sort of, but not really Gaussian, but something peaking around some value k naught. So you can do a Taylor series expansion around it. So omega of k is omega of k naught plus, and then you can write k minus k naught, the first derivative, plus additional terms, which we can say is negligible. And then you can say, okay, let's write it as the first order. So omega of k is omega of k naught plus k minus k naught vg. Now, if you go back to the function at the bottom that we had, now what we're going to do is replace this w with its Taylor series expansion. But in the Taylor series expansion, this w of k naught is a constant, and this k naught is times vg is a constant. So then the e raised to I terms for those come out of the integral, and effectively they become phase terms, right? And then you have integral dk, phi of k e raised to I kx minus, and then w is basically kvg, excluding all the other constants. So you get kvgt, then you can pull out a k, and then you get x minus vgt. So this is as if it's, you know, this. So then this gives you the impression that this is a group that's moving with this group velocity v. So this is a wave train kind of thing. And so if you have a peak, you know, it repeats. Its periodicity is given by this group velocity. So that's kind of the interpretation of this system. Now there are there are these equations of motion that we use here, you say I h bar d psi by dt, this wave function equals Hamiltonian times psi. Now this, if you look at it, there is I is an imaginary, h bar is a constant, real, and h is the Hamiltonian on the right side of the equation, which is the total energy in the system. That's a real number also. So you have I times some real and then some and a function d psi by dt, and then equals h psi. And so psi cannot be real, because if psi was real, the right hand side would be real, d psi by dt would be real, h bar would be real, and you have an I. So any solution for psi must be a complex function. Now the the Hamiltonian, is something that you try to optimize. Say, let's say you're trying to find the minimum energy in a system. So you're trying to target that. So you're trying to minimize that. Let's say you have a utility function for resource allocation, or for you're trying to solve a traveling salesman problem, or you're trying to do map coloring. Whatever you're trying to do, the energy that you define, that becomes the Hamiltonian of the system. So psi must be complex, and typically what you can observe are real things. So what you observe are probabilities, and those probabilities are proportional to mod psi square, which is psi times psi conjugate. And I'll give you an interpretation of what these probabilities are. They relate actually to energy. So, but we'll come to it in a bit. So, so you can write now psi of x comma t. We said that you could write it as integral dk, this phi k e raised to I kx minus omega t. But so now is this equation, I h bar d psi by dt equals h psi valid? So if you try to differentiate, you will get I h bar into I omega, and you get minus and times psi of times psi. So then minus I square, it is actually plus 1, and then h bar omega is h nu, which is the energy. So yeah, you do find that I h bar d psi by dt is h psi, okay? And psi was complex. Now, also there is, you might have seen Schrodinger's equation. The free particle Schrodinger equation is given at the bottom. I h bar d psi by dt equals minus h square by 2m d2 psi by dx square. But let's see whether this guy is actually equal to this. So if you take the second derivative, you pull out this guy, and you pull it out twice, and so you get minus k square psi. And then if you multiply 8 minus h squared by 2m, you get h squared k squared by 2m. And so then that becomes p squared by 2m, and so then you get that's equal. This is the energy. So then you get E psi, and we just showed E psi is I h bar d psi by dt. So that's how you write this as the equation that the wave function satisfies, the particle satisfies. Normally, if you have seen wave equations, you have seen d2u by dt square equals c square dtu by dx square. In quantum systems, you only have a first derivative with respect to time. So this sort of governs the system, the behavior of these particles. So that was just some preliminaries. Just wanted to get a feel for what's actually happening to these things. But now, whatever this whole integral is, we just say, okay, let's just represent it as this with this representation, and this is called a ket representation. And so you have this vertical line and the psi and the greater than sign. So this is a wave function of a particle, and with two states. Trying to move something. Okay. Yeah. So this is the wave function of a quantum particle, and let's say, and these kinds of representations with e raised to I kx minus omega t, these are linear, so you can actually combine two different possibilities to actually have a linear superposition. So you can have one which is describing wave function for this 0, and then you have another for 1, and then you can linearly combine them and say that you could be in a linear superposition of states. And like, let's say in the double slit experiment, the photon is actually in a linear superposition of two different paths that it could take, and then it will figure out which path it might actually take when you measure it. So now these alphas are the amplitudes, and they can be complex in general, such that, modulus alpha 1 square plus modulus alpha 2 square equals 1. So these are some of the state probabilities. They're also given by the product of the conjugate times itself. So there's another thing, like for example, I wanted to give an interpretation of what these probabilities are. So if you have a photon and it's polarized, then its electric field is oscillating in a particular direction, and the magnetic field is oscillating in perpendicular to it, and the photon is actually moving in a direction perpendicular to both. That's called the pointing vector, the direction which the wave is moving. So the direction of the electric field is the polarization, okay? And it's perpendicular to the direction of propagation. Now, if this photon arrives at a polarizer with an electric field of magnitude A, and it arrives at an angle theta, then A cos theta becomes the amplitude of the electric field that is transmitted through the polarizer. So now the energy of the wave, is proportional to the square of the amplitude, and hence the energy of the wave that is coming out of the polarizer is proportional to cos squared theta. So cos squared theta is a fraction of energy that gets transmitted past the polarizer. And so the probability, if you have a bunch of photons impinging on the polarizer, the probability that they're going through is proportional to cos squared theta. And so that's where, because that is the effective energy that is going through. So there's this probability of cos squared theta for these photons to go through. So, but the way you can write the superposition is that you have the photon initially, and it has an amplitude cos alpha. This is the amplitude of the electric field, and it has a component along the x direction. Let's say the polarizer is letting stuff in the x direction through. Has a component perpendicular in the y direction, and that has an amplitude proportional to sine alpha. Beyond the polarizer, you say the state is fixed. It's just the photon semicolon x. It's only that, but a fraction of the energy went through, and that's proportional to cos squared theta. But when you write the wave function for it now, it doesn't have any term here. This thing probability is 1. But the fraction that went through is given by the probability before it went through. That's proportional to cos squared alpha. So I hope you got the difference, why you have the square as the probability, and yet you have an amplitude when you represent the superposition of states. So just wanted to give you guys this physical interpretation, because now we'll blindly use these kinds of things without even knowing what's going on, because what has been cutely done by physicists is they've given us mechanisms to use these quantum computers, and all you have to know is what kind of transforms you're applying there with just some matrix multiplications. But underneath, they're making all these physical transformations there for the computing to happen. Now, there's another thing about measurement in these systems. Now, we said it's in a superposition of states, this quantum particle. You cannot really access the state. I mean, but if you have a whole bunch of quantum particles, you could measure each one of them, and then based on these measurements, you could assess what the probability of that of the system of photons being in a particular state could be. But you cannot ask what is this. What are the probabilities of a particular photon at any given time without observing it. And the moment you observe it, you only get one of those states. It collapses to one of the states. So if you had state 0 or state 1, it will collapse to one of them. So, but what you can do is, if you don't observe, if you have the patience to not observe, then you can fool around with this quantum particle. You can transform it in the quantum domain and do fun things with it. And then when you're ready, you actually make an observation, and it will collapse to a state. Now, any prior information is lost about all the superpositions and the probabilities. Just like, you know, after the polarizer, the only state that was there was in the direction of x. Right? So the state after measurement is the collapse state. Right? And there's a parallel statement to this, that is that since you actually don't know what the superposition nature of the the probabilities for a given particular quantum particle, you cannot actually clone any quantum particle. And if you really want to tap into it and see it, you're going to measure and it's going to collapse instantly. So now, what is this zero? How do you do this computation? So you represent, say, 0 as a 0 state as a vector 1, 0, and state 1 can be represented as 0, 1. So you could write this wave function as alpha 1, 1, 0 plus alpha 2, 0, 1. Or you could also write it as, alpha 1, alpha 2. But typically, you keep it in terms of the basis vectors. Now, we know that, the squares of these amplitudes are the probabilities. So if the squares are the probabilities and they're equally likely, then the probabilities are halves. So these amplitudes are square root of those probabilities, so they will be 1 over root 2. So this is a typical representation of a wave function, which has 0 and 1 both equally likely. But you could have a negative probability, or you could have an e raised to j theta divided by square root of 2, and things like that with some phases. But if you take this squared and add them up, you should get 1. So let's say you have another particle, then you can write it similarly, beta 1, 0 plus beta 2, 1. The sum of the state probability should equal 1. Now you can ask the combined state of these two particles, because you want to, each particle is essentially a quantum bit, but really you want to work with multiple quantum bits. So you have to think about a combined state of multiple particles. So let's say what the combined state of two particles would look like. So then you have what's called a tensor product, and it's very simple. I'll explain in just a bit, but essentially write this wave function for the first guy, and then the wave function for the second guy, and then just take each of these 4 terms. So alpha 1, beta 1, 0 with 0, alpha 1, beta 2, 0, product 1, alpha 2, beta 1, 1 product 0, and alpha 2, beta 2, 1 product 1. What are each one of these guys? Let me show you what they are. And this is a simplified notation, so it's pretty cumbersome to write it. So you just write it as 0, 0, 0, 1, 1, 0, 1, 1. Okay. So then you can write the combined state as this: alpha 1, beta 1, 0, 0, alpha 1, beta 2, 0, 1, and so on. And if you take these probabilities, square all of them up, you will find that the sum of the probabilities. So you have 0 is 1, 0, then 1 is 0, 1. How do you do this tensor product? You take, let's do 1 times 0. 1 is represented as 0, 1, right? That is here. So you put down the column vector 1, 0, 1, and then multiply each one of the elements of state 1 by the column vector for state 0. So 0 multiplies 1, 0, and then 1 multiplies 1, 0. Then when you do that, you get 0, 0, and then 1, 0. So 1 product 0 gives you 0, 0, 1, 0. And then 0 product 1 gives you 0 is 1, 0, right? And 1 is 0, 1. So you get 0, 1, and then 0, 0. And similarly, you get 0, 0 is 1 times 1, 0. 0 times 1, 0, you get 1, 0, 0, 0. And here you get this guy pulls out a 1 at the bottom. So you have these 4 things, but essentially this became a 4-dimensional column vector. Each qubit, it was a 2-dimensional column vector. Now with with 2 qubits, now we have a 4-dimensional column vector. That's all this is. So the tensor product 0, 0 is written like this, 1, 0, 0, 1, 1, 1, and so on, right? Now, so that was the tensor product. There's another terminology, it's called the bracket beta product. This is called the, if you have the wave function A, this is called bra A, this is called ket A, and this is called the bracket operation or the inner product. But this is shortened to this with just one vertical line, and it's the inner product of these two. But the way you get the inner product is you take this column vector and take its transpose if it's all real, but you take the conjugate transpose typically, and then multiply. So conjugate transpose gives you a row vector times the column vector for B, and you get a value, which is the inner product. So yeah, I just wanted to make you familiar with these things. So if you're reading it, it becomes easier for you to follow. Then what happens is, now we saw that, okay, we have 2 qubits represented as a 4-dimensional column vector, right? Or a single qubit is a 1-dimensional column vector. What you do in a quantum computer is now you manipulate these bits. So you apply matrices on these bits, but these matrices are required to be unitary in nature. That is, the conjugate of the matrix times itself should be the identity. And then you fool around with these kinds of unitary matrices, trying to do some transformations and lead the quantum algorithm to a solution. Now H here, like if you consider this H is like the Hadamard gate, it's defined like this, and it has a very interesting thing in terms of its operation. But let's check if it is unitary. So if you take H plus H conjugate H, which is just H times H, you multiply the 2, and you get half 2, 0, 0, 2, and you get that. Okay, so the H is unitary. Now we said we're going to fool around with these quantum bits, right? By applying matrices. What happens if you apply it to a 1, 0 state? If you multiply it out, you get 1 over root 2, 1, 1. There's a 1, 1 and a 1, 0, so you get a 1 over root 2. And this is also pulling out a 1 over root 2 times a 0. But with the state 1, this minus is going to get pulled out. So you have 1, 1 times 0, 1, you get a plus 1 over root 2, and then 1 minus 1, 0, 1, you get a minus 1 over root 2. What direction is this in? This is 1 over root 2, say along x-axis, and 1 over root 2, say along y-axis. This is like 45 degrees, right? So what happened? And this guy is minus 45 degrees, right? So we can geometrically see what this is. But what happened here is essentially this the qubit went into a superposition of states by using this gate. So actually, let's say we're doing some quantum computation and you did a measurement. So that collapsed the state, right? Now you want to transform it into superposition. You can apply a Hadamard gate that brings it back to superposition. So 0, 1 goes into a 1 minus 1. So geometrically, what's happening? So you had 0, and it went out here, 45 degrees, this plus 45, right? And then 1 went all the way down here, it turned all the way here. So this went anti-clockwise, and this went clockwise this way, 135 degrees. So, you know, these things are rotating funnily. How do we represent this? So there's an interesting way to think about it. You can draw the angle at pi by 8, 22.5 degrees. And you can say, hey, 0 reflected around this here. And one reflected around the same direction, went down here because this is 45 plus 22.5, and then another 45 plus 22.5, and you get 135. So one interpretation is a reflection around the direction pi by 8. And so if you write a matrix to represent that, that becomes a Harder-Mud matrix. There's another interpretation you could do, which is you could rotate clockwise and then reflect around 0. So you could rotate clockwise and then go here for 0. And for 1, you could rotate again 45 degrees clockwise and then reflect around 0. And that suddenly gives you the 135 degrees shift. So these are two different interpretations. And then if you write a matrix for rotation clockwise and then a reflection around 0, the product of those two will give you a reflection around pi by 8. So, so there are different ways to kind of interpret these transformations. Now we said this Hadamard gate is unitary. So what happens if you apply it again? You know, if you just talk about the reflection, then it just goes back, right? It just go back to where they were. But if you think about the rotation by pi by 4, then 0 has come out here. Now rotate clockwise, it comes to itself, and then you reflect. It's on itself, reflect around its original direction, and it's where it is. So yeah, it comes back to where it is. What about 1? 1, you have to take another 45 degrees down, and then reflect it, it'll go back up, right? So when you apply the Hadamard matrix again, you get back you get back the identity, and it's unitary. And so similarly, there are other gates as the identity matrix. There are Pauli matrices for which represent actions on photon spins and things like that. This one, if you look at it, it actually flips the state. It's also called the NOT gate. It's the identity gate. Now, there is another very interesting gate called the C0 gate. And what it does is it flips, it works on 2 qubits. And it flips a target qubit if a control qubit is a 1. So let's say the first qubit is a control qubit. So if it is a 1, then you would flip the second one, but it's a 0 here, so it's not going to change between these two. It's a 0 here, it's not going to change between these two, but it's a 1 here, so this guy's going to flip. And it's a 1 here, so this guy's going to flip. So what it does is it flips the 1 0 to 1 1 and a 1 1 to 1 0 with the corresponding probabilities. So that's what the C0 gate is. Very interesting. It'll help in entanglement. In just a couple of minutes, you'll see how that works. So in general, though, you have multiple states. They can be represented as a superposition of all of these states, whether some of the probabilities have to be equal to 1. And if you need m equals 2 raised to k states, then you need k qubits, right, to represent the state. So you could have a single bit quantum register, that's a qubit. We already studied that, 1 0 0 1. These are the amplitudes. But you know, you really want to have fun with qubits, multiple of them. So you need so let's say you have a 2-bit quantum register. Then you have alpha 1, alpha 2, alpha 3, alpha 4, and sorry, you should be 1. So that represents the state of a 2-bit quantum register. And what about a 3-bit quantum register? Then you would have an 8-bit column vector. And if you think about the tensor product, it's, let's say you have a column vector of 4 bits, and then you have a 2-bit column vector acting on the 4-bit, and you end up getting an 8-bit. So you produce a 3 qubit register. So that can be represented as this. These are the amplitudes, the squares of the probabilities. So there's another interesting phenomenon called quantum entanglement, where 2 photons can become entangled, and even as you separate them, they remain entangled until you make a measurement in one of them. And even if you separate them over distances, they'll remain entangled. And if you make a measurement on one of them, then the other one um, state gets fixed, also collapses. So, so collapse on one of the qubits forces a collapse on the other one. Now, you could you could say, hey, if, you could have this entanglement as direct entanglement, that is like these state values match 0, 0, 1, 1. So this means that, hey, it's either they're both 0 or they're both 1, and you don't have a 0, 1 or 1, 0 option. So this represents the combined wave function for the two particles that are entangled. And the thing is, though, once you measure it and you observe them and their states collapse, after that, they'll no longer be entangled. So you'll have to actually bring them together to actually entangle. So, but you can see that you cannot separate these wave functions out. You don't have 0, 1, 1, 0 kind of things. They remain coupled and entangled. And, collapse on one collapses the other. You can have, inverse entanglement also. So you can have flip things, because maybe you have particles of opposite spins that are created. And then you can have multiple entanglements also, multiple 4-particle entanglements and stuff like that. But how do you create these entanglements? You can apply the Hadamard to one qubit and then apply the CDOT. So if you, and follow this closely, then you really can understand what a quantum computer is doing. We know that the Hadamard, go back to Hadamard. This is what the Hadamard did, right? It took the 0 to a plus 45 degrees, and it took a 1 state to a minus 45 degrees. So now come to this computation. So let's say we apply the Hadamard on the second bit here, right? So this 0 is going to become a combination of 1 over root 2 and with the 0 state and the 1 over root 2 with the 1 state with the gamma 1 probability. So you can see 0 is going 0 over root 2 and 1 over root 2. And then there's another 0 here. That's also going 0 over root 2, then so with the gamma 3. So 0 over root 2 and then 1 over root 2. The gamma 2 is acting on the 1. 1 is going to the minus 45 degrees, right? So that's 0 over root 2 and then minus 1 over root 2. And similarly for 1, 1, this 1 is going into gamma 4, 0 root 2 and minus 1 over root 2. Now, okay, I kept these gammas different so that you can see what's going on. But now if they're all equal, if all these gammas are equal and they're all equal to half because, if you square them, you get 1/4 and 4 1/4 equals 1. So if you let them all be equal, then the 0 ones cancels out with this one, and the 1 1 cancels out with this one, and you're left with 1 over 2 root 2 0 0 twice, then gets you 1 over root 2 times 0, and then 1 over root 2 1 0. But really, when you wanted entanglement, you're almost there, but you really wanted this guy to be a 1. And what does 1 do? When the control bit is a 1, it flips this guy. So you just apply the C naught to this. And this, if you take this as a control bit and you flip this, you get this one. And you've got entanglement. But you don't see this, the thing is, for us as scientists, as engineers, we don't have to worry about how this is done. We have to tell the physicist, hey, do the C naught operation for me on the quantum computer, and they'll do it for you. So now we are at a level of abstraction where we just have to work with matrices and vectors and products, tensor products and things. So typical quantum processing basically, does transformations on these qubits. The probabilities get refined. the measurement is taken, the state collapses, and higher probability state is more likely to become the collapse state, as you evolve. I'll explain why you will actually reach there. And this process can be iterative. You might do some processing on a classical processor and then use a quantum processor to do its quantum computation. It could be a one-step thing, or you could do a repeated thing. You do a measurement and then modify it. It Shor's algorithm for integer factorization is one such thing that does a combination of classical and quantum. But we said, hey, this higher probability state is more likely to become collapse state, so that, hey, we get a good solution quickly. But how do we make that happen? And the key is magnitude amplification by transformations. There's an algorithm called Grover's algorithm. And let me quickly walk you through it. So what happens is when you have, let's say you have n items, each with state xi, and you're searching for one of these items, and you basically want to find k. So what you do is, so you have the state xi for each of the items, and xk would be the item that you want to get. So now you create a quantum state, which is a superposition of all of this with the weighted probabilities, and if they're all equally likely, then you'd have 1 over square root of n. Why 1 over square root of n? If you square it, you get 1 over n, and there are n of these things. So sum all of that, you get a 1. So 1 over square root of n, summation of all these states, right? So that is the wave function superposition. Now you note that this psi, which is superposition of all the states of the items, contains the item you want to find. And they are all equally likely. So how are you going to find it? So what you do is you define an oracle function that acts on it such that it only changes the sign for this item. It flips it, leaving the amplitudes for the other states unchanged. So all the other states remain with probability 1 over root 10, except for xk, which will flip to minus 1 over root 10. Then what you do is you actually reflect this resultant state with respect to psi. What that happens is, let's say this guy was on the positive, above the positive, or above the x-axis, let's say. It goes down below the x-axis, and then you reflect it over a much bigger angle, and then it becomes much more positive and results in an enhanced amplitude for this, while the other state amplitude's reduced. And as you repeat this process, it increases the amplitude for xk, and it favors it over time. I have the math for it here. So what happens when you actually flip, when we said we want to, make this minus the state of xk minus 1 over root 10. You had plus 1 over root 10, right, for xk, so you might subtract twice that. And so this is the effective state when you flip xk. Then you apply what's called a reflection transform, which is given by this. And this is the ket, and this is the bra, and then then this is the identity. So when you apply this, you will end up getting these terms. This thing is acting on psi, and this thing is acting on xk. Now, this is an inner product that is actually 1, because there are n items, and 1 over square root of n square root of n. This product is a 1. When psi acts on xk, it pulls out its probability, and you get 1 over square root of n. So when you simplify this, you get 2 psi minus 4 over n psi, and then I identity acting on this, you just get minus psi and then plus this. And so you get 1 minus 4n psi plus 2 over square root of n xk. So what has happened to xk? It has this stuff 2 over root 10, but it's also part of psi. And there inside psi, there is a 1 over, it has a probability 1 over root 10 times 1 minus 4 over n. So its probability is actually 3 over root 10 minus a small number, approximately 3 over root 10. So its probability went up from 1 over root 10 to plus 3 over root 10. And while all the other states went into 1 minus 4 over n times 1 over root 10, thus this guy got amplified, all the other guys get reduced. And now when you repeat this, let's say you repeat it about square root of n times, then the measurement is very likely to pick out xk with high probability. So this is how you try to steer the algorithm to pick out the answer for you. So we're almost nearing the end of the quantum part. But so there are different types of quantum computers. These are general quantum computers. They'll do any kinds of processing with all these gates and stuff like that. IBM, Intel, Google. Then there's another type of quantum computer which does annealing, but it's restricted in the sense the qubits there only talk locally to nearby qubits. If, say up, down, left, right, but may interact with a few qubits left and right and a few qubits up and down. So it's an array, and you can have a lattice of these qubits, and these are all chilled to absolute zero, and you could try to search for the lowest energy point in this landscape. And so the system tries to explore all possibilities simultaneously. That's what happens with quantum computation, because you have the superposition of states, you're exploring multiple possibilities simultaneously. This is a picture of a D-wave computer. It has a quantum processing unit, and you can have quantum machine instructions that drive it. And you can use it for optimization problems. For example, you can define qubits, and these can be energy terms. And let's say you're trying to minimize the energy for this, and these can be different qubits. Then you're effectively trying to minimize X transpose QX, and so what do? You can, here's an example of a simulation that I've done here. So you have, let's say 4 qubits, but these QI, XI are the self loops on the qubits. So these are 3.4, 4.5, 2.1. What this is saying, if you only have self loops, it is saying, don't pick 0, don't pick 1, don't pick 2, but pick 3, because that's going to reduce the energy to -2.4. Now you say, okay, but actually there are couplings. So 0 is coupled to 1 and 2, 1 is coupled to 2 and 3, and so on. And but we said, hey, 2 self-coupling is 2.3, but 2 coupled with 3 has a -3.22. So actually it's advantageous to actually set 2 also to a 1. But what about 0? 0 has a 3.4. If you couple it with 3, you get a -2. And if you couple it with 2, you get a +3.4. So yeah, 0 is looking bad, and 1 is even worse. So at the end, when you try to run this algorithm, it ends up assigning 0, 0 and 1, 1. So assigns 1 and 1 to 2 and 3. And the energy, that's the minimum energy. So what do? You in the system, you set up the qubits with their coupling values, and you let it run. And then when you let the system evolve, it ends up at the minimum state. It gives you the energy of that state. And you can do a similar thing. This has 5 qubits and similar arguments, and this one ends up with 1, 0, 1, 1, 1 with its minimum energy. So, and these are some of the some references that are there. This book is really good. The second one is really good for quantum computation and stuff. First and third are more physics related, and there are lots of lectures online, Wikipedia, D-wave documentation, and so on. So that was about quantum. And I think we only have a minute for blockchain. So let me just say, hey, I also covered it before, but essentially blockchains, they're basically, what you're trying to do is as transactions processed in these virtualized infrastructures, you want to be able to share information. You want transparency, you want traceability, you want immutability also, and so on. So, so the key features are immutability, consensus, provenance. You can have history associated with this data. But the main mechanism is to chain hashes to kind of create immutability. And then there are what are called, and so you write them into ledgers, and then you also have smart contracts. This is a Merkle tree. It just creates a root hash for a whole bunch of transactions, and then the stop hash you can use for the block. I think you might have. Sorry, let me just walk you through this here. So there can be a whole bunch of consensus algorithms. But the key thing is there are also smart contracts that run in these systems, and um, um, and these smart contracts can have some smart logic that's associated with it that all these nodes agree upon. And so there's some software that's executing that all the nodes agree upon, and then they record the information onto this blockchain ledger. And many use cases can be enabled, not just financial related, but any transactions related to any of use cases, whether it's healthcare or education or real estate and so on. What we have done is we have created a distributed virtual DLT network of nodes in our infrastructure and a virtualized infrastructure. And so we can connect them up, programmatically, and then so we can create a VDLTN, which is a network of VDLTNNs, and then we can create blockchain ledgers, and we can create ledgers for a subset of them. We can execute smart contracts, things like that. So, and also we have lazy replication that we allow, so we can have a local blockchain network that's operating at the edge of a 5G network or a 6G network, and then periodically could publish something to Kafka to remote ledgers as well. So we've enabled these kinds of infrastructures. One example is, say, for healthcare, you could be, patient maybe falling ill. You have IoT, monitoring the state of the patient. Patient is driven to the nearest hospital for emergency service. But while that's happening, the patient data could be transferred to the hospital that's going to serve the patient, whereas the data records might be somewhere else. But because the blockchain ledger is immutable, you don't put the actual patient data on the blockchain, but you could put a hash of the data on blockchain, and you can record the occurrence of the event on blockchains. It's more of a control plane kind of recording things that have happened with a trace of the information without the actual information. And you can have a smart contract that gives the consent. It could be having pre-authorized for this emergency situation, or a family member could enable it. But also do insurance processing, so that by the time the patient reaches hospital, the patient is ready for service. And this is the last slide. So in general, you can see that as 5G, 6G, and all evolve, the fun is going to be in all these applications, whether it's IoT or utilizing AI, ML, or blockchain, or quantum. And 5G can dynamically allocate resources for all of these kinds of services. IoT systems can be monitoring and providing triggers. Smart contracts can be executed for the distributed automated intelligence, and blockchain platforms can record these events. And also enable relevant actions to be taken. And in general, you have this distributed smart networks delivering timely and useful services to people. But when quantum also plays a role with all the data that's coming in with large volumes of data, and you want to do maybe the local optimization at the edge, maybe you're trying to optimize the path that a drone is going to take or something like that. Or you want to do dynamic resource allocation at the edge for a network slice at the edge. You could be using, this constrained optimization using a quantum computer or a quantum-inspired computer. So that's all I had. Thank you. And questions?
It's really very great. This is so much of mathematics and simplified in such a easy way. It is very, very great. Thank you, Dr. Dilip. It is a new dynamics you have taken people to understand quantum processing and so on. So very nice explanation and understanding. Thank you very much. So audience, if you have any query, any question, you can ask. Meanwhile, I think in a window, there is a question. If I understand and if you understand, let me see. A priori 384 SHA is assumed as a strong measure against vulnerability of blockchain process in non-quantum scenarios. How does it looks like in quantum computing?
Right. So when we talk about quantum affecting blockchain hashes, we are worried about the vulnerability of the hashing algorithm. So typically SHA-256 has been used, and going into the quantum realm, it's recommended that SHA-512, the SHA-3 based SHA-512 algorithm be used. Actually, to attack, you need about 1/3 of qubits to attack the algorithm. So 256, if you take 1/3, you're getting close to 80 plus, right? But 85.33 or something. And if you noticed, the qubits are at like 53 and 72 and things like that. So it's getting close. So current quantum computers are getting close to hitting SHA-256. But if you need to hurt 512, 1/3 of that is 170 points, 0.66, right? So you need at least 171 qubits to hit that. That's going to take a long time. So for many years, I think if we just keep, at least from now on, if we keep recording the hashes at 512 bits using SHA-3, so use SHA-512 will be fine.
Oh, that's good. There is another question. Gentleman ask whether the quantum internet using quantum teleportation is possible in future.
I don't know. Maybe it's Star Trek like, but yeah, I have no idea. It's possible, I guess.
Okay.
But with these kinds of entanglement and things like that, entanglement has been shown to work. You've been able to transport and and it's actually used for key distribution and things like that. And if as you separate the entangled bits, if one node measures, then the other entity also gets a copy of the entanglement bits. So effectively, you get a key by just tapping into those. Yeah, but I'm not sure about teleportation. But in the near term, I think definitely key distribution, those kinds of things are possible.
Okay. So if as a layman one ask what are the advantages we are going to have with quantum computing or quantum computer or quantum process? So a very layman answer. I mean,
Yeah. So if you notice this wave function, we write as a superposition of states, right? So you can think of it as, normally when we try to solve a problem, let's say we start with some initial state, and then maybe you do some gradient descent and go down, find some minimum. And then maybe you would try again, and maybe you do some annealing or whatever, but you try again, you get maybe some other local minimum, and you keep repeatedly trying. What the quantum process says is to try many things simultaneously. But also, just like we had this amplitude magnification, right? It starts pulling something out. You could argue that, hey, I could just run the same classical algorithm on many different computers and let it all finish, and I'll take the best answer out of all of them, right?
Okay.
But the quantum thing with superposition, what you will try to do is, as you're trying out many different possibilities concurrently on maybe different virtual machines, you let them interact and then maybe pick out some of the paths that are more relevant and then keep attacking. So that kind of thing. So there is somebody did a work on recommendation systems. It was highlighted in an article by the National Academy of Sciences in the US, where they reduce the processing time by actually doing this kind of concurrent superposition kind of processing. But then you have to imagine data structures that have all possible states and then the data structure is evolving, right? Normally we start with this initial state and then we just study the system. But think of the initial state with a data structure which is a combination of many different possibilities, and you keep evaluating that. That requires us to write algorithms slightly differently. And but so we could think quantum inspired when we try to do that and see if we get better algorithms.
Okay, so the one is speed you are trying to say, and many time you mentioned the energy, right? So
yeah. So if you map it into this annealing kind of computer, so then you have all of these couplings that are there, and you let the system evolve, and it will reject some of the state assignments so that the energy gets minimized, and it takes you to an allocation of the bits that minimizes the energy, and that could be used for different kinds of algorithms, including like map coloring and so on. So um, essentially that annealing type of thing works with like local connections. When you have vertices with have limited edge connectivity, neighboring edge connectivity, then you can set up like this graph with which has um, a small number of edges per node, right? And then that can be mapped to this annealing kind of computer. So, but it's not it's an approximate computation that happens, as long as the degree of these vertices is small. And it takes you to an answer quickly. But the IBM, Google, Intel kind of computers are more general computers. They'll do any computation that you want, but you have to connect up all the gates and manipulate with the qubits and things like that. So,
okay,
this tries to do some approximate computation fast, so for optimization.
Okay, and from my side, just one more question. When do you think that in nearby this is going to come at and in particular application, this is going to be used very large state. So when do you think that when it is going to come, and in which application priorly it will be accepted?
So actually, if you think of our virtualized infrastructure, we can think of some quantum algorithm-based microservices, and we could potentially just run quantum-inspired microservices purely in software, even without touching a quantum computer.
Oh, okay.
But we could also talk to a quantum computer, let it solve something, some optimization problem, that hybrid thing, the classical versus the quantum computers. On the classical side, you would have a microservice that's running on our Kubernetes cluster or something, but it will talk to some quantum computer, which will do some computation, send its measurement back, and things like that. So we could have both scenarios. I think also these kinds of entanglement-based systems also, for key distribution and quantum error coding and things like that. Those are possibilities. The only thing is that you are not allowed to measure, because the moment you measure, this quantum state is gone, it collapses. So you have to be very careful, and these qubits have to be kept super cooled, and you have to manipulate with them. And actually, they're also error prone. It's not like they do the computations perfectly today, and so there are also some efforts that go on which try to identify which qubits are more reliable. And there are people that are designing compilers to actually map computation to the more reliable qubits at any given time to actually have more reliable result. So, but yeah, I think if we start thinking differently in terms of concurrently exploring many different possibilities at the same time, as if think of yourself as a quantum particle trying to explore many things at the same time. Like you're multitasking, you're searching many different directions at the same time, but also try to have those results interact with each other, so you do overall less computations, right?
Okay, that's very great. Yeah, very nice. Any other question from audience or participant, panel members? Any other question you have for Dr. Dilip? can raise hand, you can throw question here in chat or anywhere, or you can unmute yourself if you can and ask just a last chance and one question. Okay, I think there is no question. So thank you very much, Dr. Dilip. Thanks a lot for this no great presentation, mathematical details, and making us easy understand what is quantum process and so on. So thank you very much for your time, your experience, and sharing your work and experience with our participants. Thanks a lot.
Thank you, Professor Lee. Actually, I'm just learning myself, but you know, as I was understanding, I try to try to also share it with what I've understood with you. So, thank you.
Yeah. Thank you all participants. Thanks very much for your time and coming to this webinar. So again, tomorrow again we have another very good topic of NOMA. So don't miss. Join us at 7:30. Similar like today, you will find the WebEx link, correct WebEx link on the COMSOC website. So be there at 7:30 tomorrow. See you again. Thank you very much. Good night.
Thank you.
Thank you, sir. Thank you all.